Composites mark a major turning point in aircraft design. Instead of shaping metal sheets, engineers now design the material itself to match the loads the aircraft will see in service. This shift allows lighter structures, smoother shapes, and more efficient airplanes. Composites don't just replace aluminum, they change how engineers think about structure, damage, and performance. Modern aircraft are no longer just assembled. They are engineered from the material level up. A composite is made by combining strong fibers with a binding material, so they work together as one. The fibers carry most of the load, while the surrounding resin holds them in place and transfers forces between them. On their own, neither part is very useful, but together they form a material that is strong, light, and versatile. It's similar to reinforced concrete, but far lighter and far more precise. Composites are attractive because they let engineers put strength only where it's needed. By controlling fiber direction and layer stacking, designers can tailor stiffness and strength to real flight loads. This reduces unnecessary weight and improves fuel efficiency. Composites also allow large, smooth, integrated shapes that improve aerodynamics and reduce the number of fasteners. In an industry driven by efficiency, composites offer a powerful advantage. Today, composites are used extensively in wings, fuselage sections, and tail structures. Composite wings benefit from high stiffness and excellent fatigue performance, while composite fuselages reduce weight and resist corrosion. Empennage components like horizontal and vertical stabilizers use composites for strength and shape stability. In modern civil aircraft, composites can account for more than half of the structural material by weight. Metals behave the same in all directions and usually deform before they fail. Composites are different. They are directional, layered, and fail in stages. Damage may begin internally as matrix cracking or delamination before anything is visible on the surface. Instead of bending smoothly like metal, composites tend to absorb energy through internal damage. This makes their behavior less intuitive, but highly controllable through design. The biggest advantage of composites is weight reduction, which directly improves fuel efficiency and range. They are highly resistant to corrosion and do not suffer from traditional metal fatigue in the same way. Composites also allow large integrated parts, reducing joints and fasteners. When designed and maintained properly, these advantages lead to longer service life and lower operating costs. The main challenge with composites is that damage can be hidden. A small impact from a tool drop or debris may cause internal delamination with little surface evidence. Inspecting composites requires advanced non-destructive techniques like ultrasonic testing. Repairs are more complex and often need controlled curing and skilled technicians. These challenges demand new maintenance practices and specialized training.